Hello everyone, this is Rong Gu from Mälardalen University, and this is my presentation for MER21 evaluation. My research is about mission plan synthesis and collision avoidance verification for autonomous agents. I'm a PhD student at MDH, and my supervisors are Cristina Siciliano, Edward Enon, and Christian Lundquist. Part of my research is a collaboration with colleagues at MDH who are Bara Kuroklu and Afshim Ameri, and also some colleagues from UC Leuven who are Edward Baranov and Axel Lage. So first, I want to talk about autonomous agents. Autonomous agents are systems that can move and act autonomously and perceive the environment and react. Examples of autonomous agents are robots and autonomous vehicles. In our research, we want to solve two main problems of this kind of systems. One is mission planning, including path planning and task scheduling. One is dynamic collision avoidance. First, let's talk about mission plan synthesis. To realize that, first we need to calculate the paths connecting the milestones in the environment where the tasks are supposed to be carried out. So classic path planning algorithms like theta-star algorithms here are able to calculate the shortest path between two positions in the environment. However, they cannot cope with the special road conditions, such as temporary obstacles that only exist for a little while. So we use DALI algorithm to solve this problem, and DALI is short for Devices for Assisted Living. This algorithm is developed by Axel Lage and Edward Baranov from UC Leuven. We integrate their implementation in our mission planner that I will introduce later. So this algorithm DALI can deal with these heat maps like this area near the goal position, and the temporary anomalies in like this square in the environment, and some hard and soft constraints. So we integrate the implementation of this DALI algorithm in our mission planner, which also has a task scheduler. This tool is called Time-Automata-based mission planner for autonomous agents, so we call it TAMA for short. The tool automates the synthesis of mission plan and provides a grid for the users to configure their environments very easily. We also evaluated our tool in an industrial use case, like in this picture on the left top corner. It's an autonomous quarry, and it is provided by our industrial partner Volvo Construction Equipment in Sweden. The evaluation shows the applicability of our method in real systems. This shows the workflow of TAMA. We don't need to look into details now because I will show you a video later to introduce this tool. Now I just want to mention that the task scheduler of this tool, UPO, uses a model checker UPO to generate the execution traces of the agent model. So the synthesized mission plans are guaranteed to be correct. And this is what most AI algorithms lack of. Now let's look at the video. This is the grid of our tool. First, we create a navigation area for the agents to move in. Now I'm creating these forbidden areas and temporary anomalies. Now I'm adding the existing time of these temporary obstacles, and I'm adding some tasks in this environment for the agents. After that, I'm dropping some milestones where the tasks are assigned to, like what I'm doing here. And now I'm just specifying the preconditions and the execution time of the tasks and adding the vehicles into the environment. I open one existing model, environment, and I run the server side. And here it's quite fast, but I just click the button to send the request to the server side that I want to synthesize mission plan in this environment. Then the server runs UPO and all the algorithms to calculate the mission plan and send it back to the grid here, where the path planning and the task scheduling are shown in this GUI. So all the operations On the server side, automatic, which facilitates the designers of the autonomous agents work very much. However, even though Tama has provided an automatic method for mission plan synthesis, there is still one unsolved problem that is about the scalability of task scheduling. Because task scheduling is NP hard, the scale of this problem can grow up to an extent that is unsolvable very fast. Like in this table, when the number of agents are more than 5, the model checker UPO simply runs out of memory. And thus, we come up with the idea of combining model checking with reinforcement learning. The essence of this method is to use Q-learning to synthesize task schedules. And then we verify the synthesized schedules by model checking. This picture shows the number of explored states for these two methods. And Tama simply runs out of memory, while the new method called MCRL can deal with all the situations up to 6 agents. And the number of explored states are much smaller than the numbers in Tama. We have reported our result in this paper, and the paper has won the Best Paper Award of FMIX 2020. This year, we are collaborating with Mälardalen University to integrate this method in their new branch of UPO called UPO Study Go. This ongoing work will improve our method as well as their tool, and we report in this new paper, which will be published soon. Now, let's talk about collision avoidance. The difficulties of verification of the collision avoidance is twofold. First, it's an undecidable problem to verify hybrid systems because of the continuous behavior of the agents. Second, there's no general approach to verify various collision avoidance algorithms as well as various dynamics of the agents. So first, we came up with the idea of using statistic model checking with UPO SMC. We model the agent model as hybrid automata and use statistic model checking to generate the probability of satisfactions of collision avoidance. In SMC, we can also simulate the model to generate the continuous trajectories of the agents. However, if the environment has no uncertainties, it will be better to generate to get the absolute answers of this collision avoidance verification. So this year we are writing a paper about transferring the discrete model, transferring the undecidable verification of hybrid models to a decidable verification of discrete time models, and prove that if the sampling period of the discrete time models conform with some criteria, and the discrete time models satisfy some properties of collision avoidance, then the corresponding hybrid models also satisfies these properties. So in this way, we can adopt exhaustive model checking even though the vehicle model are hybrid. And we implemented the model and the method in UPO Study Go, which treats the collision avoidance algorithm as black box. So the general approach is general that is open for extension. We have also experimented our method on a newly designed collision avoidance algorithm and found some scenarios where the agents hit the moving obstacles. These scenarios will be helpful for our colleagues to improve their algorithms. And this work will be submitted soon. Thank you for your attention.